Molecular theory of gases and its applications. All right. Kinetic molecular theory of gases explains the behavior of gases. So gases are large numbers of particles behaving like hard spherical objects in constant random motion. I refer to these as points in space. But they never stop moving. They're constantly moving. The particles will move in straight lines until they collide. And they usually collide with the container walls or another particle. And so it's like billiard balls in 3D, play and pull in 3D. They're going to collide, move, then change direction. The pressure results from particle collisions with the walls. It doesn't affect the particle collisions with each other, but when they when they collide with the walls, then you get a pressure. Collisions are perfectly elastic. What that means is energy is transferred but not lost due to friction. Transferred but not lost. Now, did we say that this was ideal? Because this is not true in real gases. There is some physics. You lose friction. Friction takes energy away. The volume of particles are negligible. That means that they're so small we usually don't worry about them. At low pH, the distance between particles is large compared to the container size. Therefore, gas volume is mostly empty space. Again, we refer to these as points in space. Okay. Attractive and repulsive forces. So gases are going to be attracted to each other or repel from each other depending upon what they are. Between molecules and or the walls of the container are negligible. We'll talk about that being a problem later. Average kinetic energy of the particles is proportional to the absolute temperature in Kelvin. And what that means is it's the same for all gases at the same temperature. So at the temperature is what gives the gases their energy. So if all the gases are at the same temperature, they have the same energy. Now there are other particles associated with that, but we're not going to worry about it. This allows the relationship between the gas laws. I'm going to walk you through one, but we're not going to worry about this. In face-to-face, I give this as a writing problem. You may end up with a couple like multiple choice, but this is basically how it works. If we look at the relationship between pressure and moles, then temperature and volume is constant. So if the temperature is constant, the energy is constant, which means the speed at which the particles are moving is constant. If the volume is constant, then the distance traveled between walls or collisions is constant. So the only thing is as you increase the number of particles, you will increase the number of collisions with the walls. So as the number of collisions with the walls increase, the pressure increases. Okay, I'll do one more here. Charles's law, volume is proportional to temperature, pressure, and moles are constant. So moles is the number of particles. So here you have to keep the number of particles constant and you have to keep pressure constant, which means you have to keep the number of collisions constant. So if you increase the temperature, you're going to increase the speed of the particles. So the only way If you increase the speed, you're going to have more collisions, but you can't increase the number of collisions because of the pressure having to be maintained. So the only thing to do is increase the distance the particle has to travel before it collides. So if you increase the temperature, you increase the speed, you increase the volume so that your number of collisions with the wall stays the same. So this is how the kinetic molecular theory can explain all of the gas laws. Okay? Now, you can also relate the kinetic molecular theory explained to pressure with respect to collisions. We talked about this. So we don't care if the particles are colliding in the middle, but every time they collide with the walls of the container, that's when you feel the pressure. Think about a bouncy house. Think about a bouncy house with no windows. And you get the kids in, and then there are no windows in the bouncy house, or you're on the side with no windows. Okay, the more kids that are in there, if you put your hand on the wall, most likely the more whacks you're going to get. So you can get an idea of the number of kids, lots or few, by the number of collisions with the walls. Okay, that brings us to molecular speed. So molecular speed is where the kinetic energy is equal to 1/2 the mass times the velocity squared. So if you'll notice, these are all at the same temperature. So if they're at the same temperature, that means they're at the same energy. Now, when gases travel, it's kind of like watching cars on the interstate. You'll always have some that are really slow and some that are really fast. And you're going to get a distribution. So the lower the mass, the greater the distribution. So if you'll notice, this is the heaviest gas in this list. So it has the tightest speed. So this is the average speed. So the average speeds are going to increase as the mass decreases. But that doesn't mean that you don't have gases moving slow and moving fast. Think about driving on the interstate. The speed may be 70. How many people are doing it? Not many. Okay, so this brings us to molecular speed. So we can relate the root mean square speed of a gas based upon this relationship here. So if it's related to the molecular weight, the gas constant, and the temperature. Okay, now I'll show you what we'll do with that in just a second. The ideal gas equation is a little YANLAP that may be interesting to read over. Okay, but let's go back to the relative velocities. So remember, we had the root mean square speed was the square root of 3 RT over the molecular weight. So what we did here was we squared it. Yeah, I'm scared. Okay, so we squared it. When we square it, we get rid of that. So if you take the opposite and you take the square root, this is what we end up with again. So if we're comparing the velocities of two gases, so the rate of 1 to the rate of 2, then we put the root mean squared speed related. Well, these are constants. 3 is a constant. So what ends up happening is the rate of 1 to the rate of 2 equals to the molecular weight of 2 over the molecular weight of 1 square root of. So what this will allow us to do is compare two gases. Now, so we can compare their velocity here. So if we're looking at the average velocity of a chlorine at 21 degrees and the oxygen is given, okay, we want to calculate the average velocity of chlorine. So its rate of 1 over rate of 2 is equal to the square root of the molecular weight of 2 over molecular weight of 1. They're inverses. Okay, so we're going to need the masses. So chlorine is 70.9054 and oxygen is 31.9988 grams per mole. So if we're looking for the rate of chlorine, I'd put it on top because it's easier if it's on top. So that means we need the rate of oxygen, which is 3.25 times 10 to the 5th meters per second, is equal to the square root of the second gas is oxygen, 31.9988 grams per mole. And again, the units here will cancel, 70.9054 grams per mole. Okay, so if we look at this, we have the rate of chlorine over 6.25 times 10 to the 5th meters per second is equal to the square root of 0.4512886. So we end up with x over 3.25 times 10 to the 5th meters per second is equal to 0.671780. Again, I'd be letting the calculator carry these digits. So x is equal to 2.8 times 10 to the 5th meters per second. We started with 3 significant figures. We'll end up with 3 significant figures. And what this allows us to do is calculate the different velocities of two gases based upon their speeds and their speeds based upon their mass. They have the same energy, but their speeds will vary based upon their molecular weights. Why are we interested in that? Well, Graham's law of diffusion. Diffusion is the rate at which two gases will mix. So the rate of diffusion is proportional to 1 over the density. Well, the density of a gas is proportional to the gas's molecular weight. So basically what ends up happening is Graham's law of diffusion looks awful familiar. It's what we just did before. Now, to make it more interesting is Graham not only studied how the gases mix, but he studied effusion, which is the rate a gas escapes from a pinhole. So if you were to put a pinhole in a balloon and measure the amount of the gas that escaped, and if you had a helium balloon versus an argon balloon versus whatever, then you'd get the rate of effusion. And again, these look awful familiar because it's based upon the concept of the speed of the gas. Okay? So, one other thing to look at, this is effusion where you're escaping through the pinhole. There's your pinhole. And the other thing is, you'll encounter this a couple times, it's called mean free path. This is the distance that a particle will travel in between collisions. So as the gas goes around, you're starting here, and this is the connection with the other wall of the container. And you're like, oh, that's the net distance traveled. But notice the path goes all over the place. But you've got to start somewhere, so you figure out the distance traveled. Okay? This is effusion. This is helium, which, floats an argon. And because helium is much smaller, it's going to escape faster. So you'll see a difference in size, etc. And in this case, it'll drop down. So on this one is with the rate of effusion of a gas A and gas B are given, what is the molecular weight of B? All right, so remember it's rate of 1 over rate of 2 is equal to the molecular weight of 2 over the molecular weight of 1. Now, to make your life easier, since I'm looking for a molecular weight, I want molecular weight of B to go on top. So molecular weight of B is on top, which means I need the molecular weight of A. Okay? And we're given that 58.34 grams per mole. So if you come over here, I need A to go on top, 3.25 times 10 to the 5th. And B is 9.72 times 10 to the 4th molecules per second. Okay, so when we do this, we end up with 3.3436 is equal to the square root of the molecular weight of B over 58.34. How do you get rid of square root? You square both sides. So end up 11.1798 is equal to the molecular weight of B divided by 58.34. So molecular weight of B is equal to 652.22989 grams per mole. We used 4 significant figures, so it's 652.2 grams per mole. That would be my unknown gas. Okay? You will definitely have one like this on the test. They're not difficult. You just have to remember to square, etc. This one is effusion. An unknown gas effuses from a container at a rate of that. Under the same conditions, xenon effuses at the rate. What is the molar mass of the unknown gas? There are your choices. Now, there are two ways to work this. You can try each gas individually, but to me the easiest way is to calculate the molecular weight of the unknown gas. So we know that xenon is 131.29 grams per mole, and this is all under the square root symbol. We know that xenon would come first. That's 3762 times 10 to the minus 2. The unknown gas is 3.618 times 10 to the minus 2. So that's 1.039 is equal to X over 131.29 grams per mole. Whoops, square root of it, square both sides. So we're left with 1.081186 is equal to X divided by 131.29. So X comes out equal to 141.9489 grams per mole. Our previous one was 2 places after the decimal, so we'll keep that. 95 grams per mole. And therefore we have the molecular weight of the unknown gas. Now, the only problem with this is you're using small numbers and you have to remember to square. But this is simple diffusion and effusion. Okay? This is chemistry put to work. This one's actually really cool. This has to do with separating of nuclear particles. Uranium 238 and 235. This is how they use the centrifuges, and you'll hear on the news about the centrifuges in nuclear countries, etc. And this explains how those centrifuges work and what's going on. So this one's actually really cool to look at, and if you like nuclear stuff, it's worth reading. We have one more very small section from chapter 10, and then we will be done.